Assalamu alaikum everyone. Welcome to the PSSC complete course. This is lecture 1 and today's topic is Introduction to Power System Analysis using PSSC. My name is Hasnain Ashraf. I am a power system studies engineer with 5 years of experience in power system studies and industrial maintenance. I have been using PSSC for real world transmission planning and grid interconnection studies. PSSE is the industry standard software used by utilities, transmission companies, consultants, and top engineers around the world for modeling, analyzing, and simulating large power systems. In this course, we are going to learn power system analysis from the basics to an advanced level. We will cover both the theoretical concepts and the practical simulations in PSSE. If you want to connect with me, my LinkedIn profile is available on the screen. You can also reach me by email or phone. The details are right there on the slide. Feel free to reach out if you have any questions. Before starting the course, I would like to mention a short disclaimer. This course is independently prepared for educational purposes only. PSSC and all company names or logos shown in this course belong to their respective owners. This course is not sponsored or affiliated with Siemens or any listed organization, and the career information shared is only for general guidance. Now, let's start with the basic questions. What is a power system? A power system is a complete network that is used to generate, transmit, distribute, and finally deliver electrical energy to consumers. It starts at a power plant that could be hydro, nuclear, or solar. The plant generates electricity. After generation, the voltage is stepped up using transformers so that power can be transmitted over long distance with minimal losses. Next, the transmission lines carry that electricity over long distances, often from one city or even one country to another. Near the consumer end, the voltage is stepped on again using distribution transformers so it can be safely supplied to homes, commercial buildings, and industries. Here we have the SLD representation of a power system. Typically, power system is represented in the form of a single line diagram because it is easier to understand, model, and analyze. In PSSC, we will also model the power system using this single line diagram approach. Now, if you look at this diagram, it is representing the same power system that we discussed earlier. From left to right side, first electrical power is generated by a generator at a voltage level of 13.8 kV. After that, the voltage is increased to 220 kV through a step up transformer. This high voltage power is then transmitted over a long distance, for example, from one city to another or from one region to another. After transmission, the voltage is stepped down to 11 kV through a power transformer and supplied to the distribution network near the consumer, and the voltage is again stepped down to zero point 0.4 kV through a distribution transformer. Finally, this low voltage power is delivered to the load, which represents consumers such as homes, commercial buildings, or industries. Why do we need power system studies? Why can't we just build the lines, connect the generators, and hope for the best? As we discussed earlier, a power system is a very large and complex network. Millions of people depend on it 24 hours a day. Any mistake in planning or operation can cause serious problems. So, before we make any changes or additions to the grid, we need to analyze it through details. Now, I will explain this in more detail. Number one, generation and load integration. In a power system, whenever a new generation plant is added, for example, a solar plant, wind farm, hydropower plant, or thermal power plant, we cannot simply connect it to the grid without analysis. We first need to check whether the existing network can safely absorb and transmit that power. Similarly, when a new large load is connected, such as an industrial plant, housing society, data center, or commercial area, we need to study its impact on the system. So, generation and load integration studies make sure that any new plant or new consumer can be connected to the grid safely, reliably, and without disturbing the existing system. Next point is varying load growth. In a power system, the load is not constant, it keeps changes with time. For example, electricity demand is different during the day and night, weekdays and weekend, summer and winter, and peak and off-peak hours. Load also varies over the years due to population growth, new housing societies, industrial development, and commercial buildings. Because of this variation, engineers need to estimate how much demand will exist now and in the future. This helps utilities plan generation, transmission, and distribution requirement according to the actual and forecasted load demand. So, varying load growth studies help us understand how demand changes over time and how the power system should be planned to meet that demand reliably. Next point is power flow constraints. Each transmission line and transformer has a limit. If we push too much power through a line, it overheats and sags, or the voltage drops to dangerous level. Through PSSC, we identify these bottlenecks and ensure that power flows efficiently without violating any thermal or voltage limits. Next point is grid resilience. Grid resilience means the ability of a power system to withstand and recover quickly from disturbances such as faults, equipment failures, natural disasters, or sudden loss of generation. Power system studies help us test the grid under different stress conditions and identify weak points. These studies ensure that even if one part of the system fails, the rest of the grid can continue supply power with minimum interruption. Next one is system reliability. System reliability means the ability of a power system to continuously supply electricity to consumers without unnecessary interruptions. Power system studies help engineers check whether the system can supply the required load under normal operating conditions and also after planned or unplanned outages. So, system reliability studies help us ensure continuous, stable, and dependable power supply to consumers. Next point is voltage and frequency stability. In a power system, voltage and frequency must remain within acceptable limits for safe and reliable operation. Voltage stability is related to maintaining a proper voltage level at different buses in the network. If the voltage becomes too low or too high, it can affect equipment performance and may create operating problems. Frequency stability is related to the balance between generation and load. If generation and load are not properly balanced, the system frequency can deviate from its nominal value. The power system studies help engineers analyze voltage profile and frequency response under different operating conditions and disturbances. So, voltage and frequency stability studies make sure that the power system remains stable and within acceptable operating limits. Next point is blackout prevention and restoration. A blackout is a complete loss of power in a specific area, often caused by cascading failure, where one small fault leads to a massive system collapse. Power system studies help us identify weak points in the network before they become serious problems. Based on these studies, engineers can take corrective actions to reduce the risk of blackouts. These studies also help if a blackout actually occurs. They guide engineers how the system can be restored safely and step by step. So, power system studies help us both prevent blackouts and restore the system after major disturbances. Next point is future network planning. Power system studies help engineers plan the future development of the grid in a proper way. These studies help us decide where new substations may be required, which transmission lines need reinforcement, and which transformer may need upgrading in the future. Instead of making random network upgrades, engineers use study results to make technically sound planning decisions. So, future network planning helps utilities building a stronger, more reliable, and well planned power system for the coming years. Now, we will discuss the most popular software which we are used for power system studies. The first one is PSSC. We will discuss this software in detail in the next slide because this course is mainly focused on PSSC. Second one is ETAP, which is widely used for industrial power systems. Third one is PSCAD. It is used for EMT simulations. Next is Dig Silent Power Factory. It is used for advanced RMS simulations. The last one is Power Word Simulator, which is commonly used for education and power system analysis. In the previous slide, we discussed different software tools used for power system studies. Now, let's focus on the main software of this course, which is PSSC. PSSC stands for Power System Simulator for Engineering. It is an advanced software platform used for the modeling, analyzing, and simulation of electrical power systems. PSSC was introduced in 1976 by Siemens TTI and has been continuously evolving for almost 50 years. Today, it is one of the most trusted and powerful tools for power system analysis. Now, let me go through the key highlights. It is mainly designed for high voltage and large scale transmission networks. PSSE is built to handle networks with thousands of buses, hundreds of generators, and complex interconnections. It can simulate the entire national grid of a country in a single model. It is widely used by utilities, consultants, and research institutes. PSSC is recognized as an industry standard tool. It is used in over 145 countries around the world. It has earned this position through decades of reliability and accuracy. Now, we will discuss the major studies that can be performed in PSSC. PSSC is not only used for drawing or modeling the power system, it is mainly used to analyze how the power system behaves under different operating conditions. Some of the important studies performed in PSSC include load flow analysis, short circuit analysis, stability analysis, contingency analysis, PV and QV analysis, optimal power flow analysis, and harmonic analysis. So these are some of the key studies that engineers performed in PSSC to ensure safe, reliable, and stable operation of the power system. Next one is who should learn PSSC. PSSC is very useful for electrical engineering students who are interested in power system analysis, grid studies, and transmission planning. It is also important for power system studies engineers who are already working on load flow, short circuit contingency, or dynamic studies. Grid planning engineers can also benefit from PSSC because it helps them analyze transmission network and plan future system expansion. Researchers and academic professionals can use PSSC for power system modeling, simulations, and research-based studies. So, in simple words, anyone who wants to build a career in power system studies, grid planning, transmission planning, or power system research should learn PSSC. Now, let's discuss career opportunities after learning PSSC. In Pakistan, PSSC skills are useful in different power sector organizations. First, we have power system entities such as NGC, ISMO, and NPCC. These organizations are directly related to transmission planning, system operation, market operation, and grid control. Then we have distribution companies commonly known as DISCOs. These organizations requires engineers for planning, system studies, grid analysis, load flow studies, short circuit analysis, and network expansion planning. So, if someone wants to build a career in the power system of Pakistan, learning power system studies and tools like PSSC can be very helpful. Apart from government power sector entities, there are also career opportunities in consulting companies in Pakistan that use PSSC and regularly hire power system studies engineers. Some of the top consultants include Power Planners International, DAR Engineering, Blake Clough Consulting, NESPAR, PowerTech, and Engineers Guild. Now let's zoom out from Pakistan and look at the global picture, starting with Europe. Europe is one of the most advanced power systems in the world. PSSC is widely used across European transmission organizations and consultancies. Transmission system operators or TSO are responsible for operating and planning the high voltage transmission network. Some examples shown here are National Grid in UK, Air Grid in Ireland, RTE in France, Terna in Italy, and Tenet in Germany. Apart from TSOs, there are also consulting companies working on grid studies, renewable integration, transmission planning, and system analysis. Some examples are Moller and Polar Engineering, PSC2 Consulting, Titus Power Consulting, and EA Technology. Now let's look at career opportunities in the Middle East. In the Middle East, power system studies skills are highly useful because the region has large transmission network, fast growing cities, industrial projects, renewable energy projects, and major grid expansion plans. Transmission system operators and utilities companies such as SEC, NEPCO, DIVA, and Kahrama work on grid operation, transmission planning, and power system analysis. Apart from utilities, there are also consulting companies such as Soft Nitro Engineering, DNV, Siemens Energy, and KN Power. These companies work on grid studies, renewable integration, industrial power systems, and technically consultancy projects. Finally, let's look at Australia, another strong market for PSSE professionals. In Australia, power system studies skills are useful in transmission system operators and consulting companies. Another strong market for PSSE professionals. In Australia, power system studies skills are useful in transmission system operators and consulting companies. Transmission system operators such as Transgrid, Powerlink Queensland, Electranet, and TAS networks are involved in operating, planning, and expanding the transmission network. There are also consulting companies such as Smarter Power Solutions, Dynamica Consulting, GSMT Consulting, and MERS Consulting, which work on grid connection studies, renewable energy integration, power system modeling, and technically consultancy projects. Australia has a strong focus on renewable energy and green transformation. So, engineers with power system studies and PSSE skills can find opportunities in transmission planning, grid connection studies, and consultancy roles. Now, let's look at the course roadmap. This roadmap shows how we will move step by step throughout this course. First, we will start with the introduction part, where we will understand the PSSC interface, network case files, single line diagrams, toolbars, progress output bar, and command line input. After that, we will move to the network modeling, where we will learn how to model buses, generators, transformers, transmission lines, loads, and fax devices. Then we will move towards core analysis, including load flow analysis, short circuit analysis, transient stability analysis, contingency analysis, PV and QV analysis, and RPC analysis. After the core analysis, we will discuss advanced studies such as LVRT and HVRT, harmonic analysis, transfer capability analysis, critical clearing time, Rokov analysis, black start, and optimal power flow studies. Then we will discuss automation, where we will learn how Python scripting can be used to automate PSSC simulations. Finally, we will cover practical applications such as generation interconnection studies, renewable integrations, load supply studies, system expansion planning studies, and loss evaluation studies. So this roadmap will take us from the basic interface of PSSC to practical industry level power system studies. Please subscribe the channel and click on the bell icon to stay updated. Thank you very much.